Okay, I see attendees joining, so I'm going to kick it off. The name of this talk is Digital Twins and Climate Resilience Analytics. And I'm very happy to welcome Dr. Youngsuk Kim, who is the Senior Data Science Manager at OneConcern and has been working on risk modeling for over 15 years. In his current role, he leads resilience model development, data analytics, verification, and validation of the models. So modeling risk is an incredibly important part of climate because it is necessary for humanity to be able to prepare for the damages and protect the people and resources who are most under risk. OneConcern is certainly one of the main players in this domain. And today we'll hear about how OneConcern uses machine learning and statistics for creating digital twins and resilience models. So looking really forward, Youngsuk, and over to you.
Thank you, Prachi. Let me share my screen. Oops. Yeah, thank you, Prachi. And hello, everyone. I'm Youngsuk Kim, and I'm developing a global resilience model with the team at OneConcern. Today, I will talk about OneConcern's digital twin and climate resilience analytics and how OneConcern applies machine learning techniques to build them. And here is the outline of the today's session. And I'll introduce OneConcern's resilience analytics platform first, and it will be followed by an overview of a digital twin. Then I will talk about how we have developed the digital twin using machine learning techniques for the case of PAW network generation. And then finally, I will briefly introduce another machine learning application and conclude the session. And before we get started, here is a quote for the today's session. Yeah, I mean, we can forget certain things, but unfortunately, we cannot give up measuring the resilience of the world we are living in against changing climate and other hazards. And especially climate change is increasing the frequency and severity of extreme natural disasters. So it requires an innovative approach to address and differentiate how climate change impacts on property, infrastructures, businesses, and communities. At OneConcern, we develop a digital twin and their resilience by employing machine learning techniques and advanced statistical method, and other methods to build a platform. And this platform is for organizations, communities, private and public sectors to understand, mitigate, and then forecast the climate risk qualitatively. Here is this slide shows a simplified layout of OneConcern's resilience analytics platform. Two main components of this platform is digital twin creation and then resilience simulation. And to create a digital twin, we collect data from public sources, private sources, and even in-house data anthropology team, and apply the various modeling techniques, data modeling techniques, such as deep learning, machine learning, and statistical learning, and statistical method, and some other data assimilation method too. And after digital twin is created, we overlay climate and non-climate hazard on top of the digital twin, and then compute the impacts and recovery of all built environments, such as buildings, lifeline systems, and community we are on. And then we process the impact and recovery output to produce the resilience stats like damage ratio, such as damage ratio, downtime statistics, and recovery curves for different infra types at various return periods and planning horizons. The orange colored one in this diagram shows where we use machine learning techniques for your information. And for example, there are more details for our platform for the United States. Here, a digital twin is firstly created for the United States, which include about 160 million buildings, 170 million power poles, 230 million power line segments, about 2.7 million highway segments, and a little bit more than 500,000 bridges, and so on and so forth. And hazard or perils consider earthquakes, hurricane winds, and flood. In the case of flood and winds, we applied the baseline, which is without considering the climate change, and RCP 4.5, one of the climate change scenarios, with a view at year 2035 and 2050. And we are adding more climate change scenarios like RCP 8.5, 6.0, and 2.6 to provide a more comprehensive projection against the future climate changes. And finally, various resilience stats are computed for each permutation between digital twin and hazard, and it is processed to compute resilience data sets later on. Now, the one question you might have is that, okay, how best you can use the output from the resilience platform? And here are some use cases for that. We can identify assets at the highest risk from structural damage and infrastructure downtime from modeled patterns, considering climate changes. So we can discover the vulnerability of your community or your portfolio. And we can project downtime of infrastructure with various return period, planning horizons, and risk threshold, so that you can have a downtime insight. And we can predict the order in which the critical lifelines are most likely fail across the assets. For example, 50-year flood events, which infra fails first? Is it port or airport? And how about 100-year return period flood? Is the airport to be part of the failed infrastructure or not? So that we can know which is the weakest link that I'm dependent on my operation of business or my operation of the community. And model your risk exposure to the lens of climate change for a comprehensive view of future scenarios so that we can have a climate eye. These as a whole provide deep and holistic risk intelligence such that we can inform business continuity and mitigation planning and optimize resource allocation and intelligent mitigation investments. And we can also quantify the impact of disasters, such as climate change impact, and they enable resilience transfer, like insurance industry, they transfer risk, and then we can transfer the resilience. We are currently working with diverse sectors, including, but not limited to banks, insurance, reinsurance companies, and real estate investment firms, public sectors, of course, to best use the output here. And how the resilience analytics we are offering is different from conventional method. The left side shows the conventional way of doing things. They are focusing on the building itself, and they use mostly like less than 100 data points. So they are more focusing on damage to buildings and the downtime of the buildings and some of the empirical understanding of the utility disruption near the buildings. But unlike the conventional method, what we are trying to do is that we physically model bridges and highways, ports and airports, substation, power poles, power lines, residential buildings and commercial buildings, everything in the digital space, and simulate to understand not only building, but also infrastructure resilience, so that we can have a holistic view of the potential outcome when there is a climate change or there is an earthquake or there is any other events happening. Developing such a comprehensive resilience platform was possible as we have built a scalable data and analytics pipeline, and the pipeline used the best of the physics-based models, statistical, and the machine learning models. And the pipeline, and we apply the machine learning models to build a digital twin, and more specifically to cover the data gaps and extend the coverage and generate the synthetic data for resilience simulation and model pipelines. And second is to improve the model performance. And I will go over these applications briefly later in the section. And then the question is like, what kind of people are building this, and who are we? We are a group of people with a very diverse background. Some are from machine learning, of course, background, and hydrodynamics, information intelligence, hydrology, mathematics and statistics, structural engineering, remote sensing, geology, and so on and so forth. So we are doing pure like interdisciplinary research and then building the pipeline together to deliver more comprehensive resilience analytics platform. Now, next item is about digital twin. And digital twin is a virtual representation of built objects and maps cities, building by building, block by block, and capturing the infrastructure like power substation, power lines, bridges, port, and airport. And it needs synthesis of a vast data set. And then thanks to the digital twin we've created, comprehensive resilience analytics is possible. So without comprehensive digital twin, resilience analytics may not be possible. And it can be the source of deep intelligence and actionable insights. So there have been many challenges in developing the digital twin. So for example, like data availability. I mean, power lines, power networks are available in utility companies, but it is not available to general public. So we had to come up with some way to create a power network. Data scarcity. Some building features are available in some of the area because the government requirements or county requirement. But some other counties, they don't require certain building features registered in the county office. So in that case, it doesn't have a data, and there is nobody has the data. And some data can be obtained manually or semi-automated fashion. So scalability was another challenge we had. And then after development, getting the trust was another challenge we had. So to resolve all the challenges we had, what we did was that firstly, we applied various machine learning techniques to extend the data coverage, fill the gaps, and then basically generate the synthetic data. And then secondly, we divided big problems into small pieces and apply the best available method and data to come up with a reasonable and robust database. And finally, we performed the exhaustive validation so that to make sure that the model performance are within the acceptable level and then people's expectation. Yeah, for this section, I will present how we develop the synthetic power distribution network, which is a part of digital twin by utilizing multiple machine learning techniques. And this diagram shows the overall layout of the power system. There is a power generation station that generates electricity. And the power is delivered to transmission substation and then distribution substation. And then finally, residential and commercial properties gets a power from the distribution substation. And then as one concern, we are focusing on distribution substation, which is shaded in green. And this diagram shows a layout. This is an overview of the power network generation and simulation. So for example, like we start with the power network generation. We need the building information, we need the roadway information and substation information. And then the network is generated. And then for a given network or generated network, we overlay hazard severity and fragility curves on top of that to compute individual component failure probability and the recovery of them. And then we do a certain Monte Carlo simulation or advanced simulation techniques, apply the advanced simulation technique to come up with a recovery curve of the power system at every building in the network as an individual or as a group. And if we zoom in the first part, which is a power network generation, here is the diagram. So it starts with simulating substation information and building location and roadways. And the substation cluster is created from the input data by allocating the customer into each substation. In other words, we start creating the service area of each substation. Then the network type here, it is overhead or underground, is identified, and the power poles and lines are generated. And then finally, network optimization model runs to produce network topology and network components and attributes. The two key models here, we apply machine learning techniques, which are in yellow color or orange color. That are substation identification and distribution network type identification. So let's move to talk about them. So power substation identification. According to the public data sources, there are more than 70,000 substations in the United States. And however, the United States Homeland Infrastructure foundation level data set, which is another public data source, provides location and features for about 50,000 substations. So we need to fill the gap between 50,000 and 70,000 substations to generate a robust and reasonable power distribution network across the country. So we, well, at the same time, we need to develop a globally applicable solution, because we are currently tackling United States, but we have to go outside the United States in the future. So as a result, we employed a computer vision technique to identify additional substations. So more specifically, we applied the vision transformer model to this problem. And we had a training data set consisting of 1,500 positive samples from 6 metropolitan areas and 10,000 negative samples from area image database. And then overall pipeline is a little bit more complex because scanning the entire country is computationally expensive. So here is the diagram of the power substation identification pipeline. And we use 2 machine learning models here. But firstly, we developed a candidate suggestion model for a given region to create a list of the substation candidate locations. Again, it's because it's too expensive to scan entire country. So we wanted to have a smaller set so that we can focus on that. And we use the hist gradient boosted classifier, and the prediction was binary. And then for the candidate location, we extracted satellite images and cropped them, and then identified the substation using the computer vision model. And then we cropped 9 subgrid images for each candidate location. Then we post-process the data and then perform the validation.
Youngsuk, I was curious, like the purpose of creating digital twin at the power network level, is that essentially then to figure out scenarios around resiliency with extreme events and things like that? Or what is sort of the applied use case here?
Yeah, applied use case here is that, again, we go back to here.
Mm-hmm.
So here, we want to know what's going to be the damage ratio for building case,
Okay.
what's going to be downtime on your building, on your community, or on your county and state, and so on and so forth.
Okay.
So given any extreme events, it could be earthquake, it could be flood and then hurricane. We wanted to do that, and then to do that, we need to have infrastructure information, which is digital twin.
Yep. Thank you.
Yeah. Yeah, and we perform the image augmentation techniques with the hyperparameters tunings to find the best model, and then we are using binary entropy loss as a loss function, as this is a binary classification problem. There's some examples of model trainings are shown in the TensorBoard, and the best model, validated model F1 is around 0.94. And the right side shows an attention map of one prediction as an example. The model is correctly focusing on the substation region to support the prediction. The next item is about power distribution system identification. And there are 2 types of feed in general. One is overhead system, and the other is an underground system. The overhead system requires a lower cost and then relatively shorter repair time if there is an issue, but they are vulnerable to strong wind, earthquakes, and wildfire. On the other hand, building underground system is more expensive and takes longer time to repair if there is an issue, but inherently it is more resilient to wind and earthquake, yet more vulnerable to flood. So identification of line type is essential in understanding the power system vulnerability on the different patterns. So for this distribution system identification, we developed the CB model and statistical model at the same time. And for the central business district and high commercial zone, we apply both models through an ensemble model to improve the accuracy. For the residential and rural area, we apply the statistical learning model, which is a random forest model, to identify the line type, and that was more scalable. So again, we didn't want to apply computer vision model to everywhere because of the computational cost. This is about the computer vision model pipeline overview. We had the samples and the Google Street images, and then we trained the model, and then try to classify the line type near the building and apply it to the roadway, and then build a local system. And this is a statistical learning model pipeline. And then it was a random forest model, and we got samples from 60,000 locations across the country. And then we trained using the random forest, and then find what, and then did the validation and so on and so forth, and applied to relatively low dense area like residential and the rural area. And then next one shows the location of all the location that we sampled the data. And the purple dots means no overhead identified, and the red dot means overhead lines were identified. So as you can see from the zoom in on maps of Houston and the Florida, you can see how dense the sampling locations are. And these plots show the performance of two models respectively. Now, overall, both models show decent F1 and accuracy, yet the CV model offers a little better performance than the random forest model. And I'm going to talk about another application of ML model, which is a seismic machine learning model to predict the damage state of a building after seismic. Okay, so conventional models usually takes building features like number of stories, construction type, and year built, and one ground motion parameter. Here, people usually use spectral acceleration as an input to compute the probability of building damage states. And there are usually 3 or 4 different damage states of a building. And unlike conventional models, our seismic machine learning model takes building features, like, again, number of stories, construction type, and so on and so forth, and 6 ground motion parameters, and 1 soil information at the site, and the output from the conventional model as an input. So instead of 1 parameter, we are using tens of parameters. The input data we require is in the order of magnitude difference, of course, to improve the model accuracy. And we developed the model for the United States and Japan. And next slide shows the recent event or important event. We collected the sample or training data set. That was from 6 events in Japan, including well-known 2011 Tohoku earthquake, 1995 Kobe earthquake, 2016 Kumamoto earthquake. We also generated synthetic data because using physics-based model, because sometimes if we train the model using only ground truth data, some physical trends are not maintained. For example, when ground motion gets higher, ground shaking is higher, we expect more damage. That's the nature of physics of law. But it doesn't follow when we train the data using the sample information training set, because there are some uncertainties in the ground motion estimation and the building information as well. So we wanted to avoid such a situation. So we added the synthetic data sets as another data set for the training. So altogether, we have about 1.5 million training data sets, and we trained the data to come up with a seismic machine learning model for Japan. And here is the result from one event prediction. That is a 2016 Kumamoto earthquake. As you can see, there is a ground truth data for each damage state. And then orange bar is for fragility model, which is a conventional model using physics-based model. And the green one is our machine learning model in performance. And this is a closure. Yeah, there are many things I discovered, but there are many things I couldn't speak because of time constraint. But we have developed an innovative resilience platform at scale, and scalable machine learning models are developed to build a digital twin and impact and recovery model. And the digital twin and machine learning models enable high-resolution resilience analytics against climate risk and, of course, non-climate risk as well. And the resilience platform can address and differentiate how natural disaster affects property, infrastructure, businesses, and community. And if you look at the background, this is a real UI of our platform. If you look at the top, it says wind. That means that we are analyzing and showing the wind impact on the area in the Miami, and more specifically, it's one hotel in Miami. And the climate is on. That means the climate change scenario is applied, and the time period is 50 years. And given the time period 50 years, what's going to be the weakest link of that property? And then there's the lines linking center location to another. That means that these are the weakest link. And right side shows the downtime and threshold for different lifelines. And it shows the downtime estimation for this scenario. For power, ports and airports and highway. And then bridges, there is no downtime, but the others have decent downtime. Okay, I think that is pretty much it. Thank you very much.
Thank you. Thank you very much, Youngsuk. This is really important work. I mean, especially when you look at sort of the overall where funding is, and innovation is happening. There is a huge gap within the adaptation and resilience sectors, right? So really important work, and I'll kick it off here with a couple quick questions. I was thinking the kinds of extreme weather events and the kind of impact it has varies a lot based on localities, right? So I was curious whether the digital twin takes care of some of those nuances and really, enables those hyper-localized analysis, and what were some of the things you probably had to do for that?
Yeah, we are trying to capture the locality, especially in the digital twin development. Of course, we overlay DEM and DTM on top of that to exactly understand the flood height and then impact on the different building. So we have the DEM and each and every building as well, so that if there is an inundation, it's not applying in an aggregate manner. It applies building by building, so that we can understand the impact on each building. And the power line is also created at each and every building as well, so that we can compute the downtime or recovery curve on each building as well. So we cannot say that we 100% capture the hyper locality, maybe not. But we try our best, not just applying some uniform method across the board. We don't do that. We differentiate the impacts and recovery models for different regions, considering different design requirements and different computation or construction practices, and so on and so forth.
Right. And you were showing those, the seismic models with, like you mentioned, you've done it for United States and Japan. I was curious, what was the timeline over which you had to iterate, especially with all the training models and things like that? I just want our listeners to have an appreciation for the level of effort some of this takes.
Yeah, the overall, we also developing some models we developed from the scratch, and some models we work with academia, and some models we got the idea from the published papers and reports. So it is difficult to say from.
It is an ecosystem of innovators, working together.
That's right. The whole ecosystem, and somebody brings their past experience to this project, and I always bring my past experience to this project as well. But when we specifically talk about computer vision model for identify the substation locations, we are working on currently version 1.2 or something, and then it took version 1. It took about 6 months, and then iteration maybe a little faster. But the most of the time-consuming part was that finding the candidate list, because we don't want to scan the entire country to identify the substation. So we have a lot of iterations to understand the candidate location for substation.
So I'm curious, how did you go about doing that?
how did we identify the candidate location? Okay, so we already have the publicly available data, substation locations, and then we are kind of trying to find the nearest building, and then we also get the features of the building. For example, what is the land use, and what is the year built, and so on and so forth. And so we have the 50,000 pairs, and then based on that, we train the model to identify, identify the candidate location.
Right. That's great. I was curious, you were showing that one concerned data science team, and it had all kinds of skill sets, which to me, actually, in fact, they crossed way beyond data science. So what is your advice for someone to get into this space at the intersection of data science and built infrastructure and all kinds of other technologies?
Yeah.
How should one start? Or, is this truly a cross-disciplinary team and you bring your own specialized skill? Is that sort of how it operates?
Yeah, we have some specialists, of course. So for example, if we want to solve like structural analysis problem, we need a structural engineer, not the generalist. But I think that one of the important things is that someone who wants to learn new things and wants to use their skill set into something that people don't usually solve, it's going to be the first thing we want to have. And the second is that if there is a specialty and there is like expertise in a certain field, yes, that's going to be another one. Yeah. But I think the passion for solving a challenging problem is, I think that's the best one, or first one we have to have.
Yep, couldn't agree more. And I was thinking, I think you covered this in some of your initial slides, some of the applications. I mean, it sounds like you have a more B2B model. But I mean, I can see the applications, and you mentioned governments too. I mean, the applications for this are really wide, right? So how much of the work that you do, the specific models, are applicable, cross-applicable across these different stakeholders? Or do you have to sort of, start from scratch a little bit to cater to certain use cases?
So the approach we are taking is that there is an underlying data. And then application can be built on top of data. So data doesn't change regardless of the user base, but some users need additional analytics or additional, some framework for best use by themselves. So we are not differentiating model itself, but the application itself, it changes. And as for your, first comments that are like maybe B2B model, yes, that is correct. But at the same time, we are trying to open the user interface of this one, user interface-based model for NGOs or non-profit organizations who are trying to address the climate change risk in their low-income housing development project and so on and so forth. So, one part of the company is trying to making an engagement with those organizations so that we can help them at the same time. So that's
no, that's great to learn. That's very inspiring. It is truly, everyone coming together to solve, I think, one of the biggest challenges of this decade. So really appreciate you taking the time to join us and share your thoughts. Any last remark?
No, thank you very much. Thank you for the opportunity. I'm sure that I can have more opportunity in the future to talk about some other aspect of the framework, but this is a good opportunity for to present what we have today. And thank you very much.
That's great. Thank you. Have a good one.
Thank you. Bye.